This is Algebra Lesson 6-1, Solving Systems by Graphing. There's some very important vocabulary words in this section that we need to go through to make sure that you understand how to deal with systems of equations. The first one is a system of linear equations, which are two or more linear equations together for which a common solution is sought. That means two lines in which you're looking for one solution that solves both of those equations. The solution of a system of linear equations is an ordered pair that will make all your equations true simultaneously. If it works in one equation but does not work in the second equation, it is not a solution. In order to be a solution, it has to work in both equations or three equations or sometimes 4 and 5 equations all at the same time. Now there's some very important types of systems. We have a consistent system. That's a system of equations that has at least one solution. It could have more than one, but it has at least one. An independent system has exactly one solution and one solution only. A dependent system is a consistent system that has infinitely many solutions. In other words, the number of solutions is absolutely infinite. You can't name it. And then there's an inconsistent system, which is a system of equations that has no solutions. When solving a linear equation, there may be an infinite number of ordered pairs that are a solution to one equation. However, when you're looking for the solution to two equations, you're looking for the one ordered pair of numbers that is a solution to both equations simultaneously. Now, there's many ways to solve a system of equations, and we will be looking at 3 of them in this particular chapter. The first method to solving a system of linear equations is to do it graphically. To solve a system graphically, you need to graph both equations on one set of x and y axes, and then interpret the graphs to determine your solution. So therefore, it's really, really important, I've been harping on you guys for a while, about using a ruler and or a straight edge to draw your lines, because if you don't have your lines cross in the right spot, because you weren't neat about drawing your lines, it's going to be really hard to determine what your solution is. So let's take a look at this first set of equations. We have 2 equations here. One is y plus 2x equals 5, and the second one is 2y minus 5x equals 10. Now, the easiest way to do these solutions, to do these equations, is I like to refer to them by number rather than by saying the y plus 2x equation. So I will number my equations. So this is going to be equation number 1 here, and this is going to be equation number 2 here. That way, when I go to refer to them, I can look at them and say, you're going to substitute this into do equation 1, you're going to do this with equation 2. Well, with equation 1, the first thing I have to do is I have to get it into y equals form, okay? Because I need to get it in slope-intercept form to graph it. The easiest way to do that is to subtract the 2x. So if I subtract the 2x, I will have y equals negative 2x plus 5. Okay, we learned how to graph by slope-intercept last chapter, so we're going to use the slope-intercept to graph. So I'm going to move up here to my y-intercept point, which was 0, 5, which is right here. And my slope is negative 2 over 1, so down to right 1, down to right 1. Using my straight edge, make sure you use a good, nice straight edge. I am going to draw my line, and I'm going to make sure I graph it, extend it way throughout my graph so that wherever it happens to cross, it will be easy for me to determine. Okay, I have to just adjust this just a little bit. There we go. Now, the cool thing about it is if you label your equations 1 and 2, you can label them on the graph 1 and 2. As long as you label them over here, you can use the 1 and 2 on the graph. So this is equation number 1. Now I'm going to look at equation number 2. I could solve it for y, but I'm looking at this equation. It's almost in standard form. It's close to standard form. I'm looking at it going, wow, I can actually graph that by intercepts because if 10 is divisible by 5 and 10 is also divisible by 2. So I'm going to graph this equation by intercepts. So if x is equal to 0, I have 2y equals 10, which means y is equal to 5. If y is equal to 0, I have negative 5x equals 10. 10 divided by negative 5 is negative 2. So my 2 points are 0, 5, which is right here, and negative 2, 0, which is right here. So I automatically know right now where my point's going to be because I share a point between the 2 equations, but I still need to draw my graph. So I'm going to draw my graph, just like I drew the last one. Oh, I'm going to do a better job than that, though. tweak this, make sure it's nice and neat and tidy. Again, because I labeled it equation number 2 to start with, I can label this equation 2 on my graph. So this is equation number 2. Where do these two lines cross? They cross at the point 0,5. So I have to list that point. Just list it right on your graph as a coordinate point and then box it. So the solution to these two equations is the point 0,5, because the point 0,5 is a solution to both of these equations. How do I know this? I can check this. Okay, if I plugged in the point 0,5 into y plus 2x equals 5, okay, let's check it. I'll show you what I mean. I'm going to check this. So y, which is 5, plus 2 times 0 is equal to 5. That checks. Now let's check it in the second equation. 2 times y, so 2 times 5, minus 5 times 0 is supposed to equal 10. Well, 10 equals 10. That checks. So I do know that 0,5 is a solution to this equation because it makes both equations true simultaneously. Let's look at a second equation, second set of equations. Okay. I have the first one, y equals negative x minus 4, and the second one, 4x minus y equals negative 1. Again, I'm going to label them 1 and 2 because it makes it easy. Equation 1 is in y equals form, so I don't need to do anything with that except for interpret it. So my y-intercept is at negative 4, so that's right there, 0, negative 4. My slope is down 1, right 1. So there's my points I can graph here. So I'm going to try to get on my points here. That's pretty accurate. It's pretty decent. Really close. There we go. This is equation number 1. So I'm going to label it equation number 1. Second equation here is not written in y equals form, so I'm going to subtract my 4x. Subtract my 4x. I get negative y is equal to negative 4x minus 1, which means y equals 4x plus 1, because if I divide everything by a negative 1, all the signs change. So my y-intercept is 0, 1, so I put a point at 0, 1. My slope is 4, so I'll go up 4, 1, 2, 3, 4, right 1, up 4, to the right 1. There's my points. Get my handy-dandy straight edge. Hopefully I will draw a really straight line, who knows. I'm a little off with my line. Gotta fix it here. Just want to tweak it just a little bit. There we go. There's my second equation here. And if I look at it, I'm going to use the red pen here. Here's where they cross, right here at that nice red dot there. That happens to be at the point negative 1, negative 3. So my solution is at negative 1, negative 3. It's my coordinate point that solves both of those equations simultaneously. All right, now sometimes we're given the equation, like in problems 1 and 2. Sometimes you're given a word problem and you have to write the equations. So it's really important to pay attention to how you're going to write your equations and how you're going to graph your equations. So let's take a look at this problem, writing a system of equations. One satellite radio service charges $10 per month plus an activation fee of $20. A second service charges $11 per month plus an activation fee of $15. In what month was the cost of the service the same? Okay, so we're looking for the month and the cost. So I'm going to let x equal my month, and in this case it's going to be number of months. And I'm going to let y equal my total cost. Okay, we have two satellite radio services. So the first service, which is going to be my first equation, charges $10 per month plus an activation fee of $20. So my total cost will be $10 per month plus my $20 activation fee. So 10x plus 20. The second satellite radio service charges $11 per month and an activation fee of only $15. So their total is going to be 11x plus 15. Okay, so here we go. We have all these lovely problems here. And I'm looking at this going, it is probably not going to be really easy to graph this by ones. I'm going to tell you right now, because most likely it's going to go beyond 10 or 11 months, or it might go beyond 10 or 11 months, but it's going to go beyond some couple of dollars. We already know that the x-axis is number of months, so I'm going to put down here number of months. My y-axis is total cost, so I'm going to put over here total cost. And my total cost should be in dollars. Okay, my months I'm going to count by ones. 0, 1, 2, 3, 4, 5, 6, 8, 9, 10 is probably good. By my total cost, I'm probably not going to count by ones because we know we have an activation fee of $15 and an activation fee of $20. So I'm thinking it's probably going to be really, really handy to count by fives, right? Because 20 and 15 are both multiples of 5. So let's go with $5, $10, 15, 20, 25, 30, on all the way up. About 70. All right. Graphing graph number 1, I can use slope intercept quite easily. It crosses the y-axis at 20, and its slope is up 10 over 1. So up 10 over 1, up 10 over 1, up 10 over 1. That's an easy graph to do. That one's not too bad. So if I graph that, there we go. Make sure that that's on my points. Yep, there we go. That's equation number 1. I'm going to label that nice and neatly. Equation number 2, the 15 is easy to graph, but the 11x is not. Okay, because I can count by 5s, but counting by, and I can count by 10s, but counting by 11 might be difficult. So I'm going to pick a point. I already know that 0, 15 is a point on this graph. Okay, and I'm thinking this going, well, I want something that ends in a 5. So I need to have something times 11 end in a 0 or a 5. The only thing that's going to happen is that's if I have 5. So if I say, if I let x equal 5, okay, y is going to equal, if x equals 5, 11 times 5 is 55. 55 plus 15 is 70. So there's 2 points on my graph that I could graph. I can graph 0, 15, which is right here. And I can graph 5, 70, which is right here. Oh, what do you know? I think I found my intersection right there between my 2 points. But I got to draw my graph. So I will draw my graph. Easier said than done. Oh, I missed miserably up there, didn't I? Let's tweak this graph. There we go. And we can see that it did cross at the point 570. Oops, that's not what I wanted. I want my pen to be red. There we go. It crossed right here. So this point is 570, but this is a word problem, so we can't just name the point. We actually have to explain what that point means, because it says, in what month will the cost of the service be the same? The cost of the service will be $70. Each one will cost $70 in that 5th month. So the cost will be the same. In 5 months. And sometimes it's nice to put down that you know the cost and that what the cost is going to be. So we can also write down that cost will be. And if you read it off the graph, we know the 570. 5 is the number of months, 70 is the amount of money. So we know the cost is going to be $70. All right, now, when you graph a system of linear equations, one of three things will happen. Right now, we've had all three of our graphs. They crossed in a single point. So the lines will cross at one point and have one solution, which means they're consistent. Okay? If they cross at one point and have one solution, that means they are a consistent system. Okay? Remember, I defined those at the beginning. A consistent system is a system that has at least one solution. And in the particular instance that we were working on, all of these are independent as well because they only had one solution. The lines could be parallel. If they have the same slopes, they're going to be parallel. And if they're parallel, they're never going to cross because by definition, parallel lines are two lines that lie in the same plane and always stay the same distance apart, which means they won't have a solution. And sometimes there is no solution. Or the third thing that can happen is the lines coincide, which means one graph lands directly on top of the other graph, which means you'll have infinitely many solutions, which means any answer to that's on the line of the first graph is also on the line of the second graph, which means it's also consistent and dependent, excuse me. So the first one here, this will give us what we call a consistent graph. And sometimes an independent one. The second one gives us an inconsistent graph. And this last one gives us a consistent and a dependent. Okay, so we're going to take a look at systems that have many solutions and no solution. So we're going to graph a couple of more systems here. If we look at problem number 4, the first equation here, y equals 3x plus 2, and the second equation, 6x minus 2y equals negative 4. First equation, it's already written in slope-intercept form, so I am going to just graph it. Okay, so my y-intercept is at 0, 2. My slope is up 3, 1, 2, 3 over 1, up 3, 1, 2, 3 over 1. There we go. I'm going to graph this line. That was a terrible way of graphing this line. It's much easier to graph actually using a ruler than it is to graph on a computer. Graphing on a computer, trying to use your ruler and get it nice and straight sometimes is a little hard. There we go. So that's my first equation. My second equation is not written in y equals form, and 4 is not divisible by 6. I mean, you can reduce the fraction, but you're going to get a fraction, so we want a whole number. So let's put it in y equals form. So you'll have negative 2y will equal negative 6x minus 4, because we move the 6 over. Divide everything by negative 2, and remember, like I said, do this separately so you don't forget to do it correctly. So that gives us y equals negative 6 divided by negative 2 is positive 3x. Negative 4 divided by negative 2 is positive 2. So what do you notice? It's exactly the same equation as equation number 1, which means equation number 2 is also going to fall on the top of equation number 1. So 1 and 2 land right on top of each other, which means it has infinitely many solutions. But it's not just anything I choose. I can't choose just any coordinate point and it would be a solution. It has to be on this line. It has to be on the line of y equals 3x plus 2. So I need to say infinitely many solutions on y equals 3x plus 2, which means any point that lands on the line y equals 3x plus 2 is also a solution of 6x minus 2y equals negative 4. Let's take a look at problem number 5. Again, we have two new equations. If I look at the first equation, I know that 12 is divisible by 4 and 12 is divisible by 2, so I'm going to make it an x and y table here and solve this using intercepts. So when x is 0, 4y equals 12. 12 divided by 4 is 3. When y equals 0, negative 2x equals 12. 12 divided by negative 2 is negative 6. So there's my 2 points there. So 0, 3 is right here. Negative 6, 0 is right there. If I'm to draw my line, oh, that was terrible. There we go. That's my first equation. So I will label it equation number 1. And notice all the graphs that I have on my smartboard right now have the x and y axis labeled. If they didn't, please label the x and y axis. You know how that needs to be done. Okay, so that's equation number 1. Equation number 2 here is almost written in y equals form, not quite. I need to move the negative 1/2 x to the other side by adding it. So I will get y equals 1/2 x minus 3. So my y-intercept here is negative 3, so I go to 0, negative 3, which is this point right here. My slope is up 1, right 2, up 1, right 2. Okay. So if I was to draw this line, and of course I missed that one too. There we go. There's equation number 2. You should be able to recognize that if I look at this, up 1 over 2, up 1 over 2, this graph up 1 over 2, up 1 over 2, they have the same slope. So if they have the same slope, we know they have to be parallel. These lines are parallel, which means they're never going to cross, which means this has no solution because they never cross. So they never have anything in common, which means there is no solution. All right, nice review here. Let's take a look at this. If a system has one solution, if you look at this first graph here, you'll see a red line and a kind of a greenish blue line. They cross at one point. In this particular case, it happens to be -1, +1. They intersect at one point. The lines have different slopes. The equations are consistent and they are independent. If you look at the second one, the purple line, the lines are the same. They have the same slope and the same y-intercept. So the equations are consistent and they are dependent. That means they have infinitely many solutions. The last graph here, the red line and the greenish line, you can see that those are parallel lines, which means they have no solution. The lines have the same slope but different y-intercepts, so these equations are inconsistent. All right, closure question. How is graphing used to solve a system of equations? Okay, so how is graphing used to solve a system of equations? Please answer that closure question.